Hi, everyone. Thank you very much for having me. I'm so sorry I couldn't make it to Australia in person, but I do appreciate a lot this opportunity. Thanks to the organizers, and I hope we'll be able to meet in another opportunity. My name is Marilyn Gatica. Currently, I am postdoctoral research assistant in the Network Science Institute at Northeastern University London, and I'm also visiting postdoc in the University of Nottingham. So today I will talk a joint effort research between these two groups. And to start, I would like to mention this motivation going towards personalized treatments. So no matter if you are thinking in healthy aging or mental health or a brain perturbation, as for example, glioma, you would like to be able to give this personalized treatment to each patient, no matter if you are thinking in pills, non-invasive techniques, or invasive techniques. And the problem is nowadays this is not working for all the patients. And the reason why is because the brain is a complex organ. So if we think in this paper of 2017 of Betzel and Bassett, we can think, for example, the brain as the complex organ with these three different axes. In this axis, you can observe, for example, the spatial one, where you can start at the cellular level of going towards the whole brain. For example, here you have the temporal level where you can think about lifespan or going towards evolution. And in the other case, in the topological one, you have like local effects at the node region, for example, pairwise and so on. And at the end, the figure is more complex and we have something like this. So in order to move towards this personalized treatment, we need to start, for example, taking an image of the brain. So for example, at this step, you can think in non-invasive techniques, EEG data, fMRI data, and so on. After this, you can use your favorite tools. In my case, is higher order interactions. We will discuss a bit about it later. And after you are doing, for example, your characterization, we can move to the modeling approach. In this case, it's relevant to use also models because you are able to propose and to test different mechanisms and then moving with this toward these personalized treatments. So at this stage, we can think, for example, in non-invasive techniques as the focus ultrasound stimulation, transcranial magnetic stimulation, pills, psychedelics, or invasive techniques. And with this, we are trying to move then the brain from a perturbation state to a control or a healthy one. And during this talk, we will be focused mainly in this part here. Different characterization with data-driven approaches, particularly with high-order interactions, and then moving to the modeling approaches in order to understand the indirect effects that you are doing, in this case with focused ultrasound stimulation. So at this stage, we are saying then that in order to move to this personalized treatment, new methodologies are needed, and also mechanistic models are essential. And to start, just to mention briefly these two different concepts, when you have two different brain regions, you can think in the anatomical information that you can acquire of it, or the functional or statistical interdependencies. In the anatomical projections, make sense to think that the interactions are pairwise because you are observing the link, the path that is connecting these two different areas. However, when you have brain activity, no matter if you are using simulation, fMRI data, EEG data, there is no reason to think that you only will observe correlation between two different areas. And this is like the classical functional connectivity approach. But however, you can go beyond this pairwise analysis and observe, for example, higher order interactions that mean you would like to analyze three brain areas, four, and so on. And when you do that, you have these two different concepts that are the redundancy and synergy. In the case of the redundancy, you are saying that no matter the part of the system that you are observing, you will have exactly the same copy of information. And in the case of the synergy, you are talking about an emergent property when you observe the system together. So, for example, when we think in Remy, in the movie Ratatouille, he was trying to explain this process of the redundancy and the synergy, trying, for example, separately the cheese or the strawberry. When he did this example, he had the same experience in terms of the flavor, the texture, the smell. However, in the other case, when he tried the two of them together, he got this amazing and unforgettable experience. So with these things, we are just trying to explain the concept of redundancy and synergy in terms of REMI's experience. And coming back to the brain, I would like just to mention briefly the extent of higher order interactions. We are talking about it like a complementary approach that the classical pairwise approaches that we are using nowadays. So for example, you have here, no matter if you are doing anatomical or functional connectivity, you have different techniques from graph theoretical analysis, in segregation integration, you also have the toolbox in order to do that. However, you also have now different math and toolbox in order to analyze higher order interactions, no matter if you are doing from topology or from information theory. And I would like just to mention brief examples here, some analysis that we did in healthy aging, but there are also some applications in neurodegeneration, also transcranial ultrasound stimulation in macaques, cognition, and so on. And just to put this in the terms also of different axes, we have here the axis of the information theory, the topological one, and also the temporal result of these different patterns. And nowadays in neuroscience, using fMRI data or EEG data, you have a bunch of different applications doing this type of analysis too. And in particularly during this talk, we will be focused in the neuromodulation in humans, in particularly using focused ultrasound stimulation. Just to start motivating these different techniques, for example, these two first panels are non-invasive techniques. And in the other case, you have SEEG data that is an invasive technique. So for example, here you can observe this electrode that is inserted in the brain. However, in the two other cases, for example, in the TMS, magnetic stimulation, you have this device where you are stimulating the brain in the scalp. So you are doing cortical perturbations, and here that's me, by the way. And when you are moving to the ultrasound stimulation, you have this device that is quite smaller, and you can go to target with high precision and also subcortical and cortical areas. And also you can observe here in this figure, Cyril and Mohamed, who are pretending to do this experiment for you. And to mention some of the milestones of the ultrasound stimulation, the fair low intensity transcranial ultrasound stimulation, that meaning you are not doing any burn in the tissue, is a reversible process. This started in 2013 in humans. And up to 2022, you already have different analyses in healthy population, epilepsy, depression, chronic pain, and so on. And up to 2024 in this review, they reported that we have less than 50 human studies, but this is growing really fast. And also to mention this nice paper where they describe the neuromodulation perception by the general public, and is super positive, and in particular is also for the ultrasound stimulation. And this is important if we think that our final goal is implement this as a potential treatment. So just to introduce this team, as I mentioned at the beginning, this is an effort with two different laboratories. One is the Professor Giovanni Petri, who is my current PI at Northeastern University London, and the other one is the Professor Marcus Kaiser. So here you also have Cyril and Mohamed, the one who were doing the experiments, and you will see other faces from information theory, whole brain modeling, and so on. And to explain briefly, in this experiment, we have 22 participants. First, we measure functional MRI data in a control condition. That means we are not doing any stimulation. And then we, in another session, split the participants in two groups. In one of them, we stimulate inferior frontal cortex, and in the other one, in the thalamus, the two of them in the right hemisphere. So after that, you also record functional MRI data, and you would like to analyze the changes, the indirect effect that you are doing when you are applying this stimulation. So here at this extent, we were trying to show that independent when you are doing a perturbation in a particular area, you are changing networks, and also you are changing higher order networks. And that's why we did. So here, for example, you will analyze the results for the inferior frontal cortex, and here you will have the result for the thalamus. For the case of the redundancy or the synergy in the inferior frontal cortex, you can observe that the patterns are more localized in frontal areas, and also in the case of the redundancy is lateralized. However, for the case of the thalamus, you can observe that the redundancy is getting spread across the brain, and in the case of the synergy, you can observe an effect more localized and even marking the points of the right thalamus. But after this, we were really interested in understand these patterns and if we can predict this effect with communications model, how this stimulus is getting propagated. And we took inspiration from this paper of Keio Seguin of 2023, using SEEG data in drug-resistant epilepsy patients, and then we're trying to explain and to predict how the stimulus is getting propagated from a particular source to the target. So in this case, they tested these 5 different communicability models, going from efficiency, where you can observe, for example, the classical shortest path efficiency, towards purely diffusion, for example, random walks. But here in the middle, you have these 2 interesting cases, the search information and the communicability that are affected if you have more paths to go from one source to the target. So in one case, for example, if you have more paths, the stimulus will get diffused, but in the other one will get potentiated if you have more paths. And in this paper was super interesting because they showed that it's not the classical efficiency communications model, the one that are more explanatory, it's not the shortest path efficiency, but it's the search information and the communicability. So it's important to move from the classical efficiency communications model towards diffusion too. So they also show that it's important how near are you from the stimulated target. And also we try to do this. So we use the distance, the shortest path efficiency, search information, and communicability to try to predict the effects in the redundancy and the synergy. And from these 4, I will just show you the 2 of them that were statistically significant for us. And in this case, we obtained that the distance and the communicability were the ones that were statistically significant. There was not the shortest path efficiency. So in the case of the inferior frontal cortex, also we recovered the effects in the redundancy, and in the case of the thalamus, we recovered it with the synergy. So with this idea in mind, we propose a simple model, in this case, a Hopf model of oscillators, in order to try to explain this propagation in the brain. So there is a lot of information here, but I will just focus in the alpha parameter. And in this case, the alpha is modulating how hard you are swapping this target. So for example, here you can observe when you are doing just a small perturbation, you don't have any change. But when you start increasing it, you are doing a local effect and then it's getting spread across the brain. So no matter if you are doing inferior frontal cortex or thalamus, you have the same pattern. But the thing that was good for us is also we recovered the effect in the redundancy for the inferior frontal cortex, and we recover also the effect in the thalamus for the case of the stimulation in the right hemisphere. So with this point, we are also saying that it's important to take different insights from invasive and non-invasive techniques and learn from each other. And just to do a bit of publicity, if you are interested in these topics, we will be in the workshop on method of information theory in computational neuroscience in July the 8th and the 9th in Florence, in Italy. But also we will be at the CCS talking about the complexity in the brain in this satellite co-brain, September the 3rd. So if you are interested, please have a look of these different programs. You can take a photo of this slide too. And coming back then, I would like to mention this preprint that we just posted, going towards this integrated and computational framework for diversity-sensitive personalized medicine. And also, just to summarize what I have been saying so far, is this idea of going toward this integrated framework, starting from example from data-driven approaches toward whole brain modeling, communications model, and learning from different insights, non-invasive or invasive techniques, and also going from different perturbation in healthy population or disease or different therapies. So if you have any question or comments, please feel free to reach me out. And thank you very much again to the organizers, and thank you to all of you for your attention.